This is an e-bike drive system review, looking at the Bosch Active Line, a very popular drive system, and the less popular hub motor from Raleigh. So the first stat we have here, 250 watts and 15.5 miles per hour. That's the UK EU limit, okay, and it's not difficult to build a motor with 250 watts. So what most bikes are differentiated on is the torque. In this case, the Bosch Active Line provides 40 Newton meters, and this hub motor 25 Newton meters. Okay, so first of all, let's look at the things which is the same. The 250 watts and going up to 15.5 miles per hour. Well, is that a lot? Well, 250 watts, if you've ever been on an erg machine, a rowing machine, and 250 watts gives you a split time of about 1:51, and that's pretty fast. Okay, you'll be sweating if you're doing that, and so having that assistance is like having a fit rower riding the bike for you. But what does that actually do? Because watts don't move you. Okay, force moves you. Okay, makes you accelerate. So we need to turn watts into force to actually see what's happening. Let's start with a formula that we know. So work done is force times distance. So power is going to be joules per second. So what we're doing here, we're differentiating with respect to time. If you don't know what that means, you can think of it as dividing it by time. So joules per second would be power, which is watts. And distance divided by time is going to be speed. Okay, so 250 watts is equal to force times speed. I'm going to call that V. Okay, so let's have a look at the graph here. Okay, 250 is force times V, and you put a few values in and you can see what happens. Well, 15.5 miles per hour, if you convert that into meters per second, is about 6.94 meters per second. So at that speed, 250 divided by 6.94, so 250 divided by 6.94, I've got 36 newtons of force. Okay, so my motor can provide me with 36 newtons of force if it's running at 250 watts and I'm traveling at 6.94. If I pick other points, I plot them on here, it will look like this. Okay, so this line represents 250 watts. So if I'm traveling at 4 meters per second, my motor can provide me with 60 newtons of force. If I'm traveling at 2 meters per second, 250 watts would give me 126 newtons. So what we know is we realize as I'm increasing speed, the force that my motor can provide decreases. Okay, and this is a reciprocal relation because force times velocity is constant. Here we haven't mentioned torque yet because the Bosch Active Line has more torque, so it's got 40 Newton meters versus the E-motion hub with 25 Newton meters. The shop will tell you, adverts will tell you, the more torque gives better acceleration. But torque doesn't actually accelerate you, force accelerates you. So how do we get torque into a force? So the formula is something like this. Torque is equal to force times the lever arm. And if you are not sure, well, torque comes in Newton meters, force is in newtons, and lever arm is in meters. So the units are correct. So you can be quite confident this is going to work. So it's easier to calculate this for the hub motor, so we're going to do that first. 25 Newton meters. We want to find out the maximum force available from that. And the lever, well, the size of the wheels is 700C, so I'm going to take the lever to be the radius of the wheel around 35 centimeters, so 0.35 meters. Okay, so 25 divided by 0.35. Okay, so my motor can provide me with a force of 71.4 newtons. Okay. Okay, for the mid-drive, we have to consider the gear ratio between the front and rear cogs, and also in this bike, the internal hub gears. So the front ring is 15 tooth and the rear ring is 18 tooth. And the internal gearing at first gear, the best case, is 0.632. And you might think, oh, I think you got that wrong. The front one is smaller than the rear one. Well, actually, yes. In the Bosch Active Line, the front cog has 15 teeth. It helps amplify the torque, as we'll see. So 15 divided by 18 times by 6.632. Okay, 0.5267. This means that for one crank of the pedals, the wheels are going to go around 0.526. Torque gets amplified by this much. This mid-drive with 40 Newton meters in first gear is like having a hub motor with 75 Newton meters. 75.9 divided by 0.35 is 217 newtons. What does that look like on the graph? So first of all, let's take the hub drive. Maximum force available of 71. At low speeds, okay, I am limited by how much force I can produce from the motor, how much torque. At high speeds, I'm limited by how much power I can produce. So go back to a formula up here. At 250 divided by 71. My magic speed here is 3.5. So below 3.5 meters per second, which is around 8 miles an hour, to below 8 miles an hour, the hub drive is limited by how much force it can put out. Above 8 miles an hour is limited by how much power. Okay, how about for the mid-drive? Well, for the mid-drive, I've got available 217. At low speeds, I'm limited by how much torque I have. What is this speed? 250 divided by 217. This speed here is 1.15 meters per second. Okay, just over 1 meters per second. So above 1 meters per second, I am limited by power. I'm no longer limited by torque. And I have more torque until 3.5 meters per second to 8 miles an hour, above which the mid-drive is equally limited by power as the hub drive. Well, this doesn't seem to make sense. What's actually happening here? Okay, well, let's take a step back and realize at these top speeds what's happening. So let's say we're cruising along at top speed. Okay, we've already worked out the motor is only producing 36 newtons. Well, how much torque do you need to produce 36 newtons? Well, let's go back to our formula. To produce 36 newtons of force at this fixed lever, fixed wheel size, I need 12.5 Newton meters. So 12.5 Newton meters at 15.5 mile per hour. No matter how much torque, peak torque, the bike can produce, no matter how it's geared, if you're traveling at 15.5 miles per hour top speed and you are drawing 250 from the motor is only actually producing 12.5 Newton meters. Having more torque available, you can't use that because it's limited to this graph here, 250 watts. You cannot produce more torque. Well, you can if you chip your bike. You can get in trouble and go to prison or something like that. At low speeds, the mid-drive is better. So that means I can accelerate faster. What's the 0 to 15.5? And what is that time? How much quicker is it? Okay, up until now we've not actually talked about the physical realities of a bike, the drag and the resistance to motion. But there's a person on the bike, so you could just say, well, the person is going to overcome these for us, so we're just looking at purely what the motor could do. How do we solve this one? We know F equals ma, so we can replace m, acceleration, v. Combined of the bike and the person and the luggage and stuff is around 100 kilos. So that's 100. Acceleration, we're going to turn that into dv dt. Okay, the rate of change of velocity. If you're not sure about this, this is actually A-level math, so don't worry if you're not sure about this. This allows us to solve this equation. Okay, I'm going to do a move here. I'm going to integrate both sides, and when I do, a bit of magic happens. Okay, this is A-level maths, separation variables. I get to a formula, 2.5t equals half v squared plus c. Okay, assuming at time 0, v 0, so therefore c is going to be 0. Don't worry if you just didn't that last 10 seconds. Here's the formula. Okay, half v squared equals 2.5t. So to get to v on its own, I'm rearranging v, so I get 5t, and I just square root that. If you plot that graph, it looks like this. Now we've got velocity up the side here, we've got time over here, and this v equals 2.2 times t to the half, and it looks like this. So that means, at time 0 we're here, no speed, no velocity. As I increase my time, okay, I'm going to get faster and faster, and the top speed is here. Okay, so that's my top speed. How long does it take to get to here? Well, you'd see it takes around 10 seconds, assuming the motor is doing all the work and there's no drag. The original one tells us that below 1.1 meters per second, my acceleration is limited to the acceleration I can achieve at that speed. So it's limited here. Well, at 1.1 meters per second, okay, my gradient is representing my acceleration. So my acceleration is constant from there down to 0. I could assume that I don't get this nice steep bit, that tangent straight down. It's as if I needed to start, add that bit of time in. So that means I can get from 0 through to my target speed of 7, just over 10 seconds. My hub drive, the critical value is 3.5 meters per second. My tangent from there, extend that across. Okay, I'm going to take an additional 2 seconds, around 2 seconds.